Hi everyone, as promised, there's a video. So it's a video recording of me working through your review sheet. I may skip certain parts. Again, if you have any questions, feel free to reach out to me. I will do my best to get back to you whenever I can. I might skip around and pause this at certain points, but you can always pause it and look back at it. So first off, for number 1, so it says if P is -7,4 and Q is 2, -10, we want to find the position vectors PQ and QP. So remember, as we're doing this one, that vectors, when it comes to vectors, the direction matters. So if we want to find the position vector, we're going to find it in component form for PQ. We are going to start with Q and we're going to subtract point P from it. So 2 minus -7 in that case, we're going to get 9, and -10 minus 4, so we're going to get -14. If we, of course, do QP, and it's going to go in the opposite direction, so we're going to go from P to Q, okay, we're going to subtract, so we're going to have -7 minus 2, so that would be -9, and then 4 minus -10, so we'll get +14. So that would be the first part, and those are both in component form. So position vectors means take the 2 points, find the vectors in between them. Find the magnitude for each. So we should already have an idea that when we take the magnitude, because we are squaring both the A component and the B component, the X and Y component, we're going to get our magnitude is square root of 277, and there's nothing you can really do with that. But your magnitude for QP, because magnitude is positive, because we end up squaring both the A and the Y component, you're going to get the same thing for both of the magnitudes, for QP and for vector PQ. Okay? C, find a unit vector in the direction of PQ. So specifically for PQ, so that means we're going to take our PQ vector, and what we're going to do is take each component and divide each component by its magnitude. That's what a unit vector does. A unit vector has a magnitude of 1 in the direction of whatever vector we're talking about, in this case PQ. So we found our position vector, we found our magnitude, and now we use that to find our unit vector. Okay, and if you don't believe me, you can always take the magnitude of the unit vector, and it should be 1. So if you take the X component, square it, Y component, square it, take the square root, you should get 1. That's a good way to check yourself if you have the time. Last but not least, find the direction of each. So we want to find, do the inverse tangent for both. So if we do the inverse tangent for -14/9, in your calculator, you're going to get -57.3 degrees. But keep in mind, you want to take into account where the vector is. So our vector PQ is 9, -14. So that one's in quadrant 4. So that would be our angle. But for our vector QP, which I'm going to put it up near QP, if we do inverse tangent, because you're dividing and you end up getting the same thing, the -57.3, that doesn't mean that's the answer. Check yourself. Vector QP is -914. That's up in quadrant 2. So you need to take that angle of -57.3 degrees and you need to add on 180 degrees. So your final angle will be 122.7 degrees. So these vectors are going in complete opposite directions. They're separated by 180 degrees, which if you think about it, makes sense, right? So -914, 9, -14, okay? Okay, let's move on to 2. So for 2, it says the magnitude of our vector V is 12 and the angle is 205 degrees. Find its vertical and horizontal components. So every vector is composed of its magnitude times the cosine of its direction angle, its magnitude times the sine of its direction angle. So in order to find its horizontal and vertical component, I am going to magnitude times the cosine of 205 degrees, magnitude times the sine of 205 degrees. Okay? Now we're going to just simplify this. If you plug this in your calculator, you should get -10.9, -5.1. Remember, this is my horizontal component, and this piece is my vertical component. So if I ask for both, you can give me just the vector. If I ask for one, tell me this is the horizontal component, this is the vertical component. Number 3, if our vector V is -12, -5, find its magnitude and direction. So when they say find the magnitude, Negative 12 squared, negative 5 squared. Okay, we'll simplify it. 144 plus 25, which ends up getting me the square root of 169, which works out really nicely to be 13. So this is my magnitude, and I should have written it like this. Apologize. And then my direction. So when they say direction, they mean find me my direction angle. So we're going to do the inverse tan of the y component over the x component. Remember, that'll give me a positive. So my calculator is going to give me the angle. If I do that in my calculator, let's see, 22.6, and that'll be in degrees. The issue is that if you were to sketch this vector, negative 12, negative 5, it's not going to be in quadrant 1. So we get 22.6 degrees. Negative 5, negative 12, negative 12, negative 5 is going to be down here in quadrant 3. So what you need to do is you need to add 180 degrees to that angle. So my angle would end up being 202.6 degrees. So my direction angle, I have my magnitude, I have my vector. Okay, moving forward with problem number 4. So we're given 4 different vectors here. We're going to start with A, and we are going to do V dotted with W. So we're going to find a dot product between them. So V is 6, negative 2, and I'm going to dot that with W, which is negative 4, negative 12. Remember, the dot product, you should end up with one number. You should not end up with a vector. So when you do the dot product, you multiply the x components, and you add them with the multiplying of the y components. So negative 2 times negative 12. Follow your order of operations, simplify first, negative 24 plus 24, and we end up getting for our dot product 0. So just a reminder, when you get 0 when you do the dot product, that means that these vectors, V and W, they are what we call orthogonal to one another, which means they're essentially perpendicular vectors, okay? That is how we check to see if two vectors are orthogonal. In this case, they just asked me for the dot product. B, if we look at B, they want t plus u, so we're just adding the vectors, and then we're doing the dot product with v minus w. So the very first thing you're going to do, besides getting overwhelmed about this problem, is you're going to start and you're going to add the vectors t plus u. You're going to get a new vector, the t plus u vector. Okay, so t and u, so negative 3 plus 4, it says to add them, so add them. We get 1. 1 plus 9 is 10. So t plus u vector is just 1 comma 10. And then we could do the same thing for subtracting v minus w. Just make sure we start with v. I'm going to subtract off w. So 6 minus negative 4 is going to give me positive 10. And then the y values, negative 2 minus negative 12. Minus minus give me a plus, so I get 10, 10. Okay, so now what am I going to do with these vectors? Well, now it says I'm going to do the dot product. So I'm going to take 110, and I'm going to do the dot product with 10, 10. And again, you should just get a scalar, one number. So 1 times 10 plus 10 times 10. 1 times 10 is 10 plus 100. So I get 110. It's long, but if you just take it piece by piece, you add the two vectors first, you subtract the two vectors, and then you take the dot product, then you'll be good to go and you'll get your answer. Okay, part C. So do not forget that you are doing the magnitude. Do not just jump right in and start taking the magnitudes of things for C. Okay, simplify the inside first, just like you normally would. So we have 3t, and I'm going to write it down here. 3t, 3 times our t vector, plus 1/2 times our w vector, and then we're going to take our magnitude. So the very first thing I'm going to do is I'm going to find what my vector 3 times t looks like. So t is negative 3, 1, so it would be negative 9, 3. And then 1/2 w would just end up being, so let's look at w, let's see what that is. W is negative 4, negative 12. So 1/2 of that would be negative 2, negative 6. Okay, and now what am I going to do with them? Follow what it says. All I'm going to do is add them. So negative 9 plus negative 2, so negative 11. And then we want to do 3 plus negative 6, negative 3. And now that we have that vector, guess what we're going to do? We're going to take the magnitude of it. So it's not hard if you just take it step by step. So I'm going to take the square root, the x component, squared, plus the y component, squared, use parentheses, equals square root of 121 plus 9. So we just get the square root of, where is it? And it cut off on here, 130. Okay, and you can go through and simplify your radicals. I will ask you to leave things on the test in simplest radical form if you can, like your unit vectors and everything. Don't give me a decimal unless it's something like bearing or result vectors like the word problems, then you can give me decimals for your final answers. Okay, but I don't want to take time to simplify radicals on here. And then is there a part D? So part D says find the angle between U and V. So let's review that. So the angle that is between U and V, so the formula is the cosine of theta equals U dot V over the magnitude of U, magnitude of V. Now, if these were different angles, those would be the angles I would use here. But in this case, they ask us for the angle in between U and V, so I'm going to use U and V, my U and V vectors. So first, I need what is U and what is V. So U is 4, 9, V is 6, negative 2. Okay, so I'm just going to write them down there. And now first I'm going to start by finding the dot product between them. So 4 times 6 plus 9 times negative 2. So we're going to get 24 minus 18, which is just 6. Okay, and then I'm going to find the magnitude of U. 4 squared plus 9 squared. So that would be the square root of 16 plus, 16 plus 81, which is going to give me a square root of 97. And then I'll find the magnitude of V. 6 squared plus negative 2 squared. So that just gives me the square root of 40. And I'm really not going to simplify too much here. I'm going to be plugging in, so I can get the calculator, I can let it do a lot for me. So my dot product, I ended up getting 6 over my magnitude of U, 97, square root of 97 times square root of 40. Remember, when you go to find theta, so now to find theta, we need to take the inverse cosine of this whole mess in here. If you do not put parentheses around the denominator in your calculator, it's going to give you a domain error most likely. Okay, put an extra set of parentheses around the denominator so your calculator does 6 divided by this whole thing rather than 6 divided by that and then multiply by square root of 40. Okay, when you take the inverse cosine in your calculator, and again, make sure you're in degrees, you should get about 84.5 degrees. Okay, and last part of this problem is determine any pairs of vectors that are parallel or orthogonal. So we started with A, and we did that V and W. We found that when we did their dot product, they gave us 0. So we know that going into part E, that V and W are already orthogonal to one another, and you can actually put it like this. V is perpendicular, orthogonal to W. So that pair we immediately know. Okay, so what you could do is you can go through all those vectors, you can find the dot product between them, see which ones are orthogonal. The other vectors, again, I don't want to take time on here to do that, but T would end up being orthogonal to W as well. If you do the dot product between all of them, dot products don't take long, you will get for both of these a dot product of 0. So that's how you know they're orthogonal. How do you tell if vectors are parallel? We talked about this in class where we said that if you can multiply one vector, the whole thing, the A and the B component, by a scalar multiple, the same scalar multiple, and get that other vector, then they're parallel. So the only two vectors that do that here are T and V. So T and V are parallel because if you look at T, which I'll look at in a second, if I were to multiply T by negative 2, I would get my V vector. Okay, there's no other vectors here that if you multiply both the X and Y component by one number, you'll get the other vector. So if we look, which ones we're looking at, t and v. So if I were to take this, multiply it by -2, both the x and the y components by -2, I'd get 6, and I'd get -2. So that's why they are parallel, because one is a scalar multiple of the other. Okay, going forward with problems 5 through 8, and I talked to you about a few of you in class. So the easiest way, when you don't have a grid or anything to handle these, is to always sketch the vectors. So kind of get an idea. I like to follow it around. So for the first one, OQ. So I start at O and I go towards Q. Yes, remember the direction matters. Plus Q to R. And we want to know, is that equal to OR? So remember, when we add vectors, we add them head to tail. So wherever I start, wherever the first vector ends, the new vector should start. And the resultant would go where the first vector started to where the last vector ended. So in this case, that's exactly what happened. So this would be true. Okay. Number 6, moving to the other side. So I'm going to clear this out. Number 6, I'm going to trace it again. I'm going to use, let's see, red. So O to Q, so I'm going from O to Q, towards Q, from Q to R. And we want to know, is that equal to RP? So I'm going to go from R towards P. And I'm going to go from P to O. And if we look at this, this is not true, because one of the vectors resultant, for the first one in red, would be going from R to O. But the other vectors resultant, would be in the blue would be R to O, but in the other direction we always start. So for OQ to QR, that resultant vector would technically be going in the other direction. So since they're going in the other direction, it would be false. If they were both going in the same direction, because they clearly have the same magnitude, the same length, but they're going in opposite directions, so it would not be true. Okay, vectors, direction matters. Next one. If we add the 3 vectors, so let's add these 3 vectors on here. So we're going to have PR plus RO plus OP. And if you notice, we get back to where we started. So what would the resultant vector be equal to? Well, if you get back to where you started, the resultant vector is actually, this should be a vector. A lot of times it's in bold, it's a bold 0 called the 0 vector. If I were to add all these up, if I get back to where I started, it's actually equal to 0, the 0 vector, because it's like saying I have 0 displacement. So this would be true. Okay, if I don't get back to where I started, then we can't say it's equal to 0. And then for number 8, we have, I'm just going to do it in a different color, PO. So we're going from P towards O. And then we want to know, is that equal to RQ? And 1, we don't know, the magnitudes are exactly the same, but in this case, they're in opposite directions. So this would be false. Okay. One thing that we could do is we could also talk about the magnitude of these vectors. So we could say, oh, okay, so say these two, we were told that they were the same, we could say, oh, their magnitudes are equal, but their directions aren't if they're going in opposite directions, so their vectors wouldn't be. Okay. And just a reminder, don't forget, you can pause this and stop at any time and work out the problems and then check yourself, okay? 9, a commercial jet is flying from Miami to Seattle. The jet's velocity is 580 miles per hour. And its bearing is 332 degrees. The wind is blowing with a velocity of 60 miles per hour with a bearing of 45 degrees. So they want me to essentially write the velocity of the jet in component form, the velocity of the wind, and then when it's its true velocity and direction of the jet, that's where the resultant is going to come in. So I'm going to start with part A. And the very first thing you have to do is deal with the bearing. So I'm going to do that over here for each one. So we are in 332 bearing. So bearing starts from true north. So 332. So if we were to say, okay, 360 minus 332, and we want to eventually get standard, so we could take 360, subtract off 332, that will get us this little bit of 28, and then we could take 90 and add 28 to get our standard, because remember your standard starts here, so we want that chunk in red. So our standard angle would be 118. We could do the same thing, so this would be for the jet. For the wind, it says that bearing is 45. That one's pretty simple because that standard is also 45. So now we have our two angles. Let's jump into the problem. So our vector for our jet, it says our velocity, so we have 480 miles per hour times the cosine of our angle in standard, 118 degrees, and then we would have 580 times the sine to get the vertical component. Okay, and if we simplify this, I'm going to do it as I'm going. I'll get negative 272.3 and then 512.1. Part B, the wind. So the wind is clearly not traveling as fast, 60 times the cosine of 45 degrees, 60 times the sine of 45 degrees. And if you simplify this, you're going to get about 42.4, 42.4, same thing, okay? So now C asked, what is the true velocity and direction of the jet? So what this is saying to me is, okay, so you have your jet flying, and then you have your wind affecting the direction and the velocity or the speed of that jet. So where do they actually end up flying? What's the horizontal and vertical components? So to find the resultant, you're just going to add my wind and my jet vector. So if I add them, I will end up getting negative 229.9 for my horizontal component and 554.5. Okay, so that would be my resultant vector. They didn't ask that. They want my true velocity or my true speed. So first, to find my true speed, I'm going to find my magnitude. And I'm going to find my direction angle, but first my magnitude. So, okay, so I didn't simplify this on here, but you'll see it on your key if you just end up solving it. Your magnitude or your true speed is going to end up being about 600.3 miles per hour. And then my direction, same thing. You want your direction angle, but your direction angle of your resultant. So you just do the inverse tangent of the vertical component over the horizontal. And your calculator is going to give you, when you plug that in, negative 67.5 degrees. But again, check yourself. Negative 229, 554 should be in quadrant 3. So I need to, sorry, quadrant 2. So I need to add 180 degrees to get me that my true direction is 112.5 degrees. So I have my true speed, my true direction, and my true resultant vector. Okay, so looking at this review sheet, numbers 10, 11 have a lot to do with work. Now we just did work the other day during testing, so I'm not going to put too much work on there, so don't worry about 10, 11. Yes, they're good to know moving forward for future classes, and I can go over them after the test, but I'm not too worried about them for this assessment. Okay, so you can skip over 10, 11 if you want to try them, go ahead, but that's fine. I'm going to skip them on here. You can see them worked out. I'm not going to assess you on this test amendment. Okay, so let's go forward to number 12. So 12 says a boat heads in the direction of north 72 degrees east. The speed of the boat in still water is 24 miles per hour. The water is flowing directly south. It is observed that the true direction of the boat is directly east. Okay, so the first thing I'm going to do to solve this problem is I'm going to start out and deal with this directional. So it says north 72 degrees east. So this is essentially, they're giving it to you in bearing. I'm not going to give you anything where like you have to really guess. I would just say bearing. But it's saying, okay, north goes 72 degrees towards the east. So that means 72 degrees bearing, which in standard we know is just 18 degrees. Okay, so this would just be 18 degrees standard. The speed of the boat in still water is 24 miles per hour. The water is flowing directly south. It is observed that the true direction of the boat is directly east, so that's related to the resultant. So express the velocity of the boat in still water. So I'm just going to use B for boat. I don't know what I used on the answer key, but that's fine. So we're going to have 24, since that's the speed of the boat, times the cosine of my angle, 18 degrees. 24 times the sine of my angle, 18 degrees. Okay, and I can simplify this to get my components are at 22.8 7.83. And if I do 24 sine of 18, I'll get 7.42 approximately. Okay, so express the velocity of the boat in still water as a vector component form. So this is the velocity of the boat in still water. It is not being affected by, when it says still water, it's not being affected by the water flowing. Okay, part B. Find the speed of the water and the true speed of the boat. So the water is flowing directly south. So the only thing we can say about the water, if it's flowing directly south, okay, one of the things that we can say is that it has no x component. It's not going left or right at all. But we do not know the magnitude. They don't tell us the speed of the water. So it says find the speed of the water. So we're technically trying to find that magnitude. We know that it's flowing due south, so 270 degrees. Okay, so that's really all we know so far. And we don't even know if we need to use that yet. And then it says find the speed of the water, which we're going to solve. We can't quite solve that yet. And the true speed of the boat. Okay, one thing I forgot to mention, going back to our water vector, is that sine of 270, -1. So whatever we get for this component, so negative of the magnitude, we're essentially going to kind of find the speed of the boat right out. And we'll talk about that more when we get there. But they also tell us in the problem, going back, it says it is observed that the true direction of the boat is directly east. So the resultant, if we were to add these two together, our x component would just be the 22.83. And our y component would be 7.42. And then technically plus the negative magnitude, right? The magnitude of whatever it is, which is what we want to find. We want to find the speed. But they tell us that the true speed of the true direction of the boat is directly east. So if it's directly east, what we know is that the y component, if it's directly east of the resultant, has to be 0. So what we created for ourselves is an equation. We don't know anything about, we don't know how far it's going east. So we can't say anything about the x component. But we know if the true direction, they're telling you the true direction, the resultant vector has is going due east, that it has a y component of 0. So we have an equation we can solve here. So I'm going to subtract that over and divide. So what we'll end up getting is the speed of the boat is 7.42 miles per hour. Now, if you look on the key, it says negative. It's magnitude, so it should be positive. So you can kind of just ignore that negative on there. That would just be the speed of the water. We could not do this problem if we didn't know that the water was going, due east, or the boat was flowing due east or due north, and so on and so forth. We have to know that information. Okay, so now that we know that information, we have the speed of the water, which is the magnitude here, and we know our resultant vector has to be 22.83, 0, because we found our resultant by adding them together. And that I just totally, I left out before. I said that we didn't know that. We do. We already found our resultant. And we can find the true speed of the boat by just simply finding the magnitude. So we'll get the speed of the water, and then we'll get the speed of the boat by just finding the magnitude of r. And it shouldn't be surprising, since the y component is 0, that when you take the square root of 22.83 squared, you're just going to get 22.83 miles per hour. So I apologize, I said that you didn't know the x component of the result before. Yeah, you do, because we already found it. We already added them together. We added our boat, we added our water, and we ended up getting our resultant vector. So I apologize. Okay, so you have the speed of the water and the speed of the boat. Okay, next one. A jet is flying through a wind that is blowing with a speed of 55 miles per hour in a direction 60 degrees standard position. So my jet is going to be, let's see, with speed of 55 miles per hour in a direction 60 degrees. So I'm going to start out writing that one. Cool, so we know all of that information. And then it says that if the jet has a speed of 765 miles per hour, what direction should the pilot head the plane Okay, let's try that again. So a jet is flying through a wind that is blowing with a speed of 55 miles per hour in the direction 6 degrees standard. So we know the wind vector. All we know about the jet is that it has a speed of 765 miles per hour, but it doesn't say in what direction should the pilot head the plane in order for the course to be true north. So we don't have the angle there. That's what we're trying to find. Okay, so we don't have it for either component. So we do know for our resultant vector, though, that when we add these two, if we're going to head due north, that means that we are going to fly directly north or towards the 90 degrees, which means my x component in this case would have to be 0. My y component, on the other hand, I know the angle is going to be 90. So if I think about it, I don't necessarily know the magnitude of the resultant vector, but I know I'm going to have this sine of 90 degrees because that would be my angle due north. So this whole thing, sine of 90 is just 1, so it's just the speed, whatever the speed is. So what we're going to do to approach this is we really don't need the second part of the equation. We can just use the x components. When we find the resultant, we add the wind and the jet together, and we know that if we're going to head due north, our x component has to be 0. So we'll have 55 cosine of 60, and you could calculate this if you want to, plus 765 cosine of theta, and that has to equal 0. So the only variable in this equation is theta. So that means if I add these together, so I'm going to get that cosine of theta, if I end up simplifying it and solving, is equal to negative 27.5 divided by 765. And if I take the inverse cosine of both sides of this loveliness, the angle that I will be given is 92.1 degrees. So this is the direction that the pilot should head the plane so that it ends up flying due north. And that's the only thing this problem is asking. So at this point, what I'm going to do is I am going to save this, and then I'm going to upload the rest of the problems on a separate video. So this, I just did problems 1 through, it looks like 1 through 13. I'll do the last problems on a separate video, and I will upload both of the videos so that you can approach them. Remember, I had a few mess ups in between the last video, so if you hear me pause and kind of start again, you know, I didn't want to remake the entire video. So just be patient. If there's anything, you can always pause it, and if you have any questions, pause it, contact me, look at the review sheet, answer key, the whole nine. Okay, so I'll be uploading the second part of the video right after this video.